Okay, so we're at the end of section 1.1 here. I guess the only thing left to talk about in section 1.1 is the method of Gauss that we use to find sums. And just a little history here. So Gauss, who lived from 1777 to 1855, was a very famous mathematician. And legend has it that this great mathematician was at a very young age, and he was told by his teacher to find the sum of the first 100 counting numbers. So 1 plus 2 plus 3 plus 4 plus all the way up to plus 99 plus 100. Okay, and the teacher thought that, this would keep them busy for a while. They didn't have calculators back then. And, maybe I can get some stuff done. And so while his classmates toiled at the problem, he just simply wrote down the answer and handed it to his teacher. The answer was 5,050, and he explained how he got the problem. And so he said, okay, what probably most students would do was take 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, and if we do it like that, we're going to take a while to get to 100, okay? There's a much faster way to do this. If you take 1 plus 100, that gives you 101. 2 and 99, that gives you 101. 3 and 98, that gives you 101. 4 and 97, that gives you 101. So every time you're going to get 101. Now, how many times do you get 101? Well, if you work your way towards the center, the last two numbers that you'd be using would be 50 and 51, which when added together would give you 101. So it's going to be faster to multiply. Okay, if we take 50 times 101, we get 5,050, which happens to be correct. Okay, so Gauss was using inductive reasoning. He also saw, a pattern, which allowed him to quickly get the answer. Okay, and now that's the idea with these problems that we want to be doing here. So suppose that we want to add 1 through 400. Okay, 1 plus 2 plus 3 plus all the way to 400. And we want to get the answer very quickly. Okay, so if you take 1 plus 400, you get 401. 2 and 399, you get 401. 3 and 398, you get 401. Okay, so how many times do you get 401 is the next question. Well, there's going to be 200 times where you get 401, since the last pair of numbers that you'd be using as you work your way towards the center would be 200 and 201, which when added would give you 401. So it's going to be faster to multiply 200 times 401, which would give you 80,200. Okay? So, Gauss was a famous mathematician, like I said, and your book calls this the method of Gauss, but it's all about a pattern that you see rather than just doing the sum directly. Okay, because sadly I'll have students type in 1 plus 2 plus 3 plus 4 plus all up to 400. Okay, and that is taken way too long. So the idea is that you can get this in just a few seconds and be done with the problem. Okay. Part C, what if we have 2 plus 4 plus 6 plus, now I'm only using even numbers here, so it'll be plus 98 plus 100. Okay, well, let's see. So if I use the method of Gauss, 2 and 100 gives me 102. 4 and 98 gives me 102. 6 and 96 would give me 102. Now the question next is, how many times do you get 102? Okay, well, what some students will do is they will mess this up, and they would say, well, half of 100 is 50, so 50 times you get 102. No, you've only got the even numbers here. Okay, so half of 50 is 25. Okay, and if you take 25 times 102, you get 2,550. Now just an observation here, notice how 2,550 is not half of 5,050. Not half of 5,050. Okay, so the point is that you actually have to do work here to get the answer and not just take half of this number. Okay. Now another way that you could do it is you could factor out a 2. Okay, since all these numbers are even, let's factor out a 2. Okay, so that 2 times the quantity 1 plus 2 plus 3 plus 4 plus 5, all up to 50. Okay, and then I can use Gauss's method just on what I see inside the parentheses. 1 plus 50 is 51. 2 and 49 is 51. 3 and 48 is 51. Okay, so how many times do I get 51? Well, it's going to be half of this list, since the last pair of numbers that I'd be using would be 25 and 26, which would give me 51 when I add. Okay, so this is going to be 25 times that I get 51. I still got this 2 up front here. So if I take 2 times 25 times 51, that would give me exactly 2,550. Okay, 2 times 51 gives me 102, and I've still got the 25 out there. Okay, so now one thing that you may notice here is that in all these problems I've ended with an even number. What if we ended with an odd number? Okay, well there's a very easy way to get around that. Suppose if I had a 1 plus 2 plus 3 plus 4 plus all the way up to 125. Well, I can add the first 124 numbers together. That way I'm ending at an even number, and then whatever I get from that, I could just add 125. Okay, so let me do that first. 124 gives me 125. 2 and 123 gives me 125. 3 and 122 gives me 125. Now the next question is, how many times do you get 125? Okay, well, it's going to be half of this list. Half of 124 would be 62 times, so 62 times 63 gives you 125. Okay, so it's going to be much faster to multiply rather than to add directly. Okay, if we take 62 times 125, we'll be able to add the first 124 numbers. Now, I still got this plus 125 out front. Okay, so I need to make sure I add 125, but 62 times 125 plus 125 should be 7,875. Okay. The homework in this section 1.1 is on page 6. I'd like you to look at these problems, and again, you guys are only doing the odd numbered problems. Okay, so take that into account there. But be sure to look at those on page 6. Okay, and let's see here on section 1.2. 1.2 is kind of all about predicting the next term using what's called the method of successive differences, and then observing what the next equation would be in a formula, and then we'll also look at what's called triangular numbers, square numbers, pentagonal numbers, things like that. Okay. Now this is all in examples of inductive reasoning, okay, which we're still using. Now I'll comment on that. Section 1.2 would begin right here. Definition: an arithmetic sequence is where each term after the first is found by adding the same number. Okay, so as an example, suppose we have 5, 13, 21, 29, 37. What's the next number in that list? Well, in this list, it looks like you're adding 8 each time to get to the next term. So if I add 8 to 37, I get 45, and so I guess 45 would be the next likely term in the list. Now, a geometric sequence is where each term after the first is found by multiplying the same number. Okay, here's an example. If I have 2, 12, 72, 432, 2,592, okay, what will be the next term in that list? Well, so the thing to notice here is that I've got a geometric sequence. 2 times 6 gives me 12. 12 times 6 gives me 72. 72 times 6 would give me 432, if you were to check that. 432 times 6 gives me 2,592. Okay, so it looks like all I'm doing is I'm multiplying each of the previous numbers by 6 to get the next number. So if I continue to do that, 2,592 times 6 should be 15,552, which would be, the number that I would guess. Okay, now sometimes sequences provide more difficulty in getting the next term. Okay, consider the sequence 3, 8, 20, 43, 81, 138. What would be the next number in that list? Well, let's see. So I can't identify this as an arithmetic or geometric sequence. It's neither one of those, so I've ruled that out. Okay, what would be the next number in the list? Well, I'm going to use a method that's called the method of successive differences. What I do is I basically write the list down here that I'm given, 3, 8, 20, 42, 81, 138, okay, and then directly below that, so successive differences means that you're going to subtract the numbers that are right next to each other. It's always the right number minus the left number. Okay, so 8 minus 3 gives me 5, 20 minus 8 gives me 12, 43 minus 20 gives me 23, 81 minus 43 gives me 38, 138 minus 81 gives me 57. Okay, now I want to continue to do that until I get a row that is all the same number. Up here, I don't see all the same numbers, so I got to repeat what I just did. And it's always the right number minus the left number, by the way. Okay, so take 12 minus 5, you get 7. 23 minus 12, you get 11. 38 minus 23, you get 15. 57 minus 38, you get 19. Okay, I still don't see all the same numbers, so I got to repeat this again. 11 minus 7 gives me 4. 15 minus 11 gives me 4. 19 minus 15 gives me 4. Okay, so I'd use inductive reasoning, and I would assume that this trend continues, where the bottom row here is all 4s. Okay, so I'm going to use inductive reasoning and assume that the bottom row is all 4s. And so if I put a 4 there, okay, what would be this number? Well, it's going to be 23, since 23 minus 19 would give me 4. And then so in a way I'm going to backtrack here. Okay, I've got a 23 right here. What's this number? Well, if I add these two numbers here, 23 plus 57 gives me 80. Okay, so 80 minus 57 will give me 23. Okay, and so if I add 80 to 138, 218, or 218 minus 138 would give me 80. Okay, so 218 would be the number that you'd guess as the next term. Okay. Let's try problem 14 there. So we need to use the method of successive differences to determine the next term in the sequence. 6, 18, 37, 63, 96, 136. So what I do is I write the list again with a little space in between, and then it's always the right number minus the left number. Okay, so 18 minus 6 is 12, 37 minus 18 is 19, 63 minus 37 is 26, 96 minus 63 is 33, and 136 minus 96 would give me 40. Okay, now I don't see all the same number there, so I need to repeat what I just did. Take the right number minus the left number. 19 minus 12 gives me 7. 26 minus 19 gives me 7. 33 minus 26 gives me 7. And 40 minus 33 gives me 7. Okay, so I'm going to use inductive reasoning here, and I'm going to assume that the bottom row repeats all 7s. Okay? Now remember, in inductive reasoning, the conclusion may or may not be true. We don't care if this number is right or wrong. It's just an educated guess there. So I'm going to assume that the bottom row repeats all 7s. Okay? And this number would be 47, since 47 minus 40 would give me 7. And the next number in the list then would be 183. Okay? Since 183 minus 136 give me 47. Okay? Now, there's a note, which is very important, saying that the method of successive differences will not always work. Okay, sometimes students like what we're doing here and they use it all the time, and you don't want to do that. Okay, sometimes it won't work. Okay, for example, suppose that we have the sequence, which is a sequence that we've already seen before, called a Fibonacci sequence. Okay, 1, 1, 2, 3, 5, and 8. Okay. Well, so previously when we saw the sequence, what we're doing there is we're adding the two previous numbers to get the next number. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8. So you guess the next term would be 5 plus 8 is 13. Okay. Let's see what the method of successive differences gives us. So if I take the right number minus the left number, 1 minus 1 is 0. 2 minus 1 is 1, 3 minus 2 is 1, 5 minus 3 is 2, 8 minus 5 is 3. Okay, and I got to repeat this until I get all the same number. 1 minus 0 is 1, 1 minus 1 is 0, 2 minus 1 is 1, and 3 minus 2 is 1. Okay? Again, I almost had it, right, just that second number there. So let me repeat. 0 minus 1 is negative 1. 1 minus 0 is 1. 1 minus 1 is 0. Now, anytime you get a negative, you can pretty much stop because this method won't work for negative numbers. Okay, but let me keep going though, just to point out the big issue. So 1 minus 1, or 1 minus negative 1, same as 1 plus 1 is 2. 0 minus 1 is negative 1. Okay, repeat again. So negative 1 minus 2 is negative 3. Now, the idea with the method of successive differences is you have to have two or more terms that are the same. Okay, so that's what I had here. I repeat all 4s, I repeat all 7s. I don't repeat anything here when I get to this bottom row, so I can't assume anything. In fact, if I did try to work this backwards, the next term would be 8, which is wrong. Okay, we already said the next term is 13. Okay, so that's an issue with the method of successive differences. You got to be careful. You can't always use it. Okay, sometimes it will fail. Okay, and I'm going to go ahead and stop right there.